Drone technology is used in many industry backgrounds. Many applications can be monitoring large areas, imaging fields, and also 3D mapping.
A drone requires a flat piece of ground to land on. In the rough terrains, this is not possible. An artificial platform could be brought in and landed upon, but this platform must be adjustable to all terrains.
The senior design group was challenged with making a mobile drone landing pad. The team members include Christian Dahl, Austin Peterson, Jared Honeyman, and Nathan Stitch. This was a faculty-sponsored project, and our mentor was Dr. Inbei Zhang.
The objective of this project was to design a self-stabilizing mobile landing pad for a drone. There were two requirements. First, it must be able to detect the pose of a drone, and two, it must be able to control at least 4 degrees of freedom for roll, pitch, yaw, and the z-axis translation. We initially had 8 concepts, of which we chose concept number 3, which uses an IMU, smart actuators, aluminum rods, ball joints, and a Raspberry Pi to control it all.
The 6 smart actuators were daisy-chained together, in which they could all be controlled simultaneously with the Raspberry Pi.
The control algorithm behind the design used multiplication of matrices to relate the frames, and then an optimization algorithm to move the motors to the correct angle.
While building our pad, we went through a series of progression where we first came up with a concept, test printed it to prove a proof of concept. This can be seen in the horns that were 3D printed and the aluminum rods. In the horns, we first used an inexpensive material to first test fit how they performed. Once we were satisfied with how they performed, we moved to more expensive material which was more rigid. The same thing was done with the aluminum rods. They were upgraded from M3s to M5s. A max angle of 15 degrees was able to be reached in any direction that the platform chose to rotate in. The drone that this platform was built for weighs a little under 1 kilogram. The platform was load tested using 5 1-pound weights. The platform was successfully able to rotate and articulate under the load. We would like to thank Robin Francisco in the Mechanical Engineering Department for their help in 3D printing and machining during our project.